Which one of the following contains the smallest number of moles of carbon dioxide? Okay, so for each part we need to work out how many moles of carbon dioxide it has. So if we start with A is a mass, so we're going to do moles equals mass over mR. The mass in the question is 2.65 and the mR of carbon dioxide is 44. So that gives us an answer of 0.0602 moles. For B, we're going to use the ideal gas equation, which is PV equals nRT. We want to rearrange it for moles, which is N, so that's going to be PV over RT. Don't forget, when using the ideal gas equation, you've got to convert the units. So firstly, the pressure needs to be in pascals. So we need to times it by 1,000 to convert it from kilopascals into pascals. The volume needs to be in metres cubed, and usefully it's been given to us in metres cubed, so we don't have to convert that. We're going to divide it by the gas constant, which is 8.31. You'll always be given that, you don't need to know it. And the temperature in Kelvin. And that gives us a number of moles of 0.0596. C and D are also ideal gas equation questions. So for C, we've got 200,000 pascals times a volume of 1.5. Now this is decimeters cubed, be careful. To convert from decimeters cubed to meters cubed, you want to divide by 1,000, which is the same as putting times 10 to the minus 3. Gas constant still the same, and in this one the temperature is given to us in degrees C, so you need to convert it to Kelvin by adding 273. That gives us a total number of moles of 0.0602. Again for D, it's the ideal gas equation, so this time we've got 100,000 pascals. We've got our volume in centimetres cubed, so we need to divide by 1,000,000. And then we're going to divide that by the ideal gas constant times the temperature in Kelvin, which is already given to us in Kelvin. And that gives us a value of 0.0602. So the one that contains the smallest number of moles is going to be B. So B is our correct answer. Okay, question 2 is a bit like a partial question on working out percentage yield. We just got to work out the maximum mass. So a particular sample of iron ore contains 85% by mass of iron oxide and no other iron compound. The maximum mass of iron that could be extracted from 1 tonne of this ore is... So we're going to start with moles equals mass over mR. Now, ordinarily you should convert the tonnes into grams, but as we're going to convert the grams back into tonnes at the end, they would cancel out, so we can leave it as tonnes and not have to convert it. So this is the moles of iron ore. And we're starting with 1 tonne, and it gives us the MR in the question, so we don't have to calculate it. And it's 0.00627. Probably better written in standard form, but it's all right like that. Right, the question tells us that only 85% of the ore is actually iron oxide, so I'm going to work out what 85% of 0.0627 moles is. So we will do 0.00627 divided by 100 times by 85. You could also times it by 0.85 and that would get you the same answer. Because the formula is Fe2O3, for every 1 mole of Fe2O3 we're going to end up with 2 moles of iron. So the moles of iron are going to be double the last answer. Then we want to work out the mass. So we're just going to times that by the relative atomic mass, which is 55.8. Which gives me an answer of 0.59 tonnes. So the answer is A. In the experiment to identify a group 2 metal X, we've been given a mass of X that reacts with an excess of aqueous hydrochloric acid according to the following equation. The volume of gas given off is 65 centimetres cubed, and it gives us a pressure and a temperature. So the first thing we can do is we can work out the moles of hydrogen gas. And we're doing that using the ideal gas equation. We've got a pressure that is given to us in kilopascals, so the first thing we need to do is convert that into pascals. The volume is given in centimetres cubed, so you've got to divide that by 1,000,000 to turn it into metres cubed. Then we need to divide that by the gas constant and the temperature in Kelvin, which is equal to 2.56 times 10 to the minus 3. Okay, we don't need to worry about the hydrochloric acid because it says it's in excess, and the reason it's in excess is to make sure that all of X reacts. So we can assume that the moles of hydrogen gas given off are going to be the same as the moles of X. So that is also equal to the moles of X. Now if we've got the moles of X, we can work out the MR of X because we've been given the mass. And we do that by dividing the mass that's given to us in the question by the moles that we've worked out. And the group 2 metal that has a mass closest to 39.8 is calcium, which has a mass in the periodic table of 40. So that must mean that our metal is calcium. So the answer must be B. For question 4, we have to work out percentage mass of oxygen. So for A, we're going to take the mass of oxygen. Now there's only one atom of oxygen in this particular molecule, so that's going to have a mass of 16, and we're going to divide it by the MR of the whole molecule. So you can see all of the answers are fairly similar. Now the question asks which one contains the smallest. Well, the smallest is just about B, so the answer is B. Okay, for this question, we're going to start by working out the moles of magnesium hydroxide. So we're going to use mass over MR, which is the mass given in the question divided by the MR Okay, from that we can then work out the concentration. The moles of magnesium ions are going to be exactly the same as the moles of magnesium hydroxide, because every one of those is going to give us one of these. So the concentration of the magnesium ions is going to be moles divided by volume. We don't need to put the factor of 1,000 in because we're given the volume in decimeters cubed. So this is just checking you understand how the units work. Okay, and if we have a look at the answers, that gives us the answer D. Okay, for this next one, sodium hydrogen carbonate decomposes on heating as shown in the equation below. The volume of carbon dioxide measured at the temperature and pressure given gave us 0.05 of a mole of sodium hydrogen, obtained by heating 0.05 of a mole of sodium hydrogen carbonate is. Okay, so the first thing we need to do is to work out the moles of CO2. And if we have a look at the equation, 2 moles of sodium hydrogen carbonate give us 1 mole of carbon dioxide. So the moles of carbon dioxide are going to be half the moles of sodium hydrogen carbonate. Okay, once we've got that, we can put it into the ideal gas equation. Don't forget to correctly convert all of your units. Now, temperature is already given to us in Kelvin, so we don't need to do anything with that. Pressure, however, is in kilopascals, so we need to change that into pascals, which gives us a value of 6.13 times 10 to the minus 4. But remember, that's in metres cubed. If we want to convert it into centimetres cubed, we multiply it by 1,000,000. So that gives us an answer of A. An equation for the incomplete combustion of butane is given below. The volume in decimetres cubed of oxygen at the temperature and pressure given required to burn 0.1 of a mole of butane to form steam and carbon dioxide is. Right, so the first thing we need to do is we need to work out the moles of oxygen. And if you have a look in the equation, 1 mole of butane gives you 4.5 moles of oxygen. So if we times the number of moles of butane by 4.5, we end up with the moles of oxygen. Next, to work out the volume, we're going to use the ideal gas equation. And then put the numbers in. Temperature is given to us in Kelvin, so we don't have to do anything with that. Pressure, however, is given in kilopascals, so we need to convert it to pascals. Okay, so we get the answer in metres cubed. However, it asks us for the volume in decimetres cubed. So to get into decimetres cubed, we multiply metres cubed by a factor of 1,000, which gives me 11 decimetres cubed, which is B. Okay, the removal of silicon dioxide with limestone in the blast furnace can be represented by the following equation. Okay, so we're trying to work out the volume of carbon dioxide. We've been given a temperature and a pressure, and we've been given a mass of silicon dioxide. Now remember, when we're dealing with moles, we're actually working in grams. And we've been given a value in tonnes and kilograms, so we need to convert it. If we want to use mass over MR, we wouldn't need to do this if we were converting the final value back into a mass, but we're not. We're using the ideal gas equation, so we've got to convert this. So if it was 1,000 kilograms, that's going to be 1,000,000 or 1,000,000 grams. Divide that by the MR. And that gives us quite a few moles, but actually for 1 tonne, that's not unreasonable. And then we're trying to work out the volume of carbon dioxide. The moles are going to be the same because it's a 1-to-1 rate relationship. So that's the same as the moles of CO2. So again, we're going to use the ideal gas equation. Temperature again is given to us in Kelvin, so we don't need to do anything with it. Pressure, as usual, this time actually no, the pressure is given to you in pascals. I was about to say kilopascals because that's normally what it's given to you, but this question is being nice. Don't forget your volume comes out in metres cubed, so that gives us an answer of 408, which is option D. We've got another removal of silicon dioxide with limestone in the blast furnace question, but this time we're trying to get our final answer in tonnes. So the fact that our beginning mass has been given in tonnes doesn't matter. We can leave it in tonnes because we're going to convert the final answer back into tonnes. So we're going to work out the moles of silicon dioxide, but I'm just going to leave the mass in tonnes. You can convert it into grams if you want to, but you would have to convert from grams back into tonnes at the end. Okay, and we can see from the equations that the equation that the mole of calcium carbonate is the same as the moles of silicon dioxide. So the mass of calcium carbonate is going to be the moles times the MR, which is 1.67. And remember, we had it in tonnes to start with, so the answer is going to come out as tonnes. And that gives us an answer of C. The following equation represents the oxidation of vanadium 4 ions by manganate 7 ions in acidic solution. Don't worry too much about the fact it's quite a complicated equation. We're only using it to work out volumes and concentrations. So as long as we've got a balanced equation, that's all we need. Okay, so the question tells us how many moles of vanadium ions we've got. So we can use that to work out the moles of the manganate ions, because in the equation you can see that it is a 5:1 ratio. Okay, once we've got the moles of manganate, we can work out the volume. And we're going to use moles divided by concentration times 1,000. The concentration is given to us in the question as 0.02. And that gives us a volume of 100 centimetres cubed. And if we have a look, 100 centimetres cubed corresponds to the correct answer, which is D. Okay, question 11. Which of these pieces of apparatus has the lowest percentage uncertainty in the measurement shown? So remember, percentage uncertainty or percentage error is the error in the equipment divided by the value measured and then it's percentage, so we're going to times it by 100. This now needs working out for each one of these pieces of equipment. So you can see the one that has the lowest uncertainty is going to be this one. So the answer is A. Magnesium reacts with hydrochloric acid according to the following equation. A student calculated the minimum volume of 2.56 mole per decimetre cubed hydrochloric acid required to react with an excess of magnesium to form 5.46 grams of magnesium chloride. Which of the following uses the correct standard form and gives the appropriate number of significant figures to give the correct result of the calculation? So let's work out the calculation to start with. So we're going to start by working out the moles of magnesium chloride, which is going to be mass over MR. From that, we can then work out the moles of HCl. We know from the equation that 1 mole of magnesium chloride is formed from 2 moles of hydrochloric acid. So the moles of hydrochloric acid are going to be 2 times the moles of magnesium chloride. And then from that we can work out the volume of hydrochloric acid, or hydrogen chloride. So our volume is 44.76 centimetres cubed. Now all of the answers are in decimetres cubed, so the first thing to do is to divide it by 1,000. Then we've got to decide to what precision we should have our answer. Now if you have a look, everything in the question is to 3 significant figures. Now we can't invent precision, so our final answer should also be to 3 significant figures. So that would be 4.48 times 10 to the minus 2 decimetres cubed, which is B. A saturated aqueous solution of magnesium hydroxide contains 1.17 times 10 to the minus 3 grams of magnesium hydroxide in 100 centimetres cubed of solution. In this solution, the magnesium hydroxide is fully dissociated into ions. What is the concentration of Mg2 plus ions in this solution? Okay, so we're going to start by working out the moles. And this is the moles of magnesium hydroxide. So we'll do a mass over mR. Now for every 1 mole of magnesium hydroxide, we're going to get 1 mole of magnesium 2 plus ions. So that also is equal to the moles of the magnesium ions. We can then work out the concentration of the magnesium ions by using moles divided by volume times 1,000. And that's the concentration, so it's in moles per decimetre cubed. And if you have a look at the answers, that corresponds to answer D. Okay, we've got a substance called an ester, which is actually something you'll see next year, but what it is doesn't matter. We know it's hydrolysed, as shown by the following equation. We want to work out a percentage yield. So the first thing we've got to do is work out the maximum potential yield. So to do that, we're going to work out the moles of RCOOR. And we'll do that using mass over mR. The mass is 1 gram, and it tells us the mR is 150, so we don't have to worry about what it actually is. Okay, we can then work out the moles of RCOOH, because 1 mole of this makes 1 mole of this. And then we can work out the mass of RCOOH by doing moles times mR. And we're given the mR as being 100. So that gives me a maximum potential yield of 0.667 grams. So to find out my percentage yield, I do the mass that's actually obtained, which it tells you in the question that only 0.5 of a gram is obtained. The most I could have got is my theoretical yield, which I've calculated. So that gives me a 75% yield. And 75% is answer D. A student is provided with a 5 centimetre cube sample of 1 molar hydrochloric acid. The student is then asked to devise a method to prepare a hydrochloric acid solution with a concentration of 5 times 10 to the minus 4 moles per decimetre cubed by diluting the sample with water. Okay, so the way we're going to start this is by working out how many moles of HCl we have to start with. So if we haven't got the moles, we're not going to be able to work out how much water we need to add. So it's a vol times conc divided by 1,000, which gives me 5 times 10 to the minus 5 moles. I then want to work out the total volume of solution needed. And to do this, I'm going to use the moles I've just worked out, divided by the concentration I want to make, times 1,000. So I find I want 100 centimetres cubed. Now the question asks how much water I need to add. I start with 5 centimetres. And I want to make 100 centimetres cubed, so I need to add 95 centimetres cubed. If we have a look at the answer, then 95 is answer B. Which of the following contains the most chloride ions? So we're going to have to do the same calculation for each one of these. So it's going to be a volume times conc divided by 1,000 to work out the moles of each substance. So for aluminium chloride, if you do that concentration, you end up with 0.00033. Again, standard form may have been better there, but not to worry. For calcium chloride, we end up with 0.001. For HCl, we end up with 0.00099. And for sodium chloride, we end up with 0.001. Now, you've got to be a little bit careful because the question's asking about chloride ions. For aluminium chloride, for every mole of aluminium chloride, we're going to get 3 moles of chloride ions. So this one needs timesing by 3. This one, for every 1 mole of calcium chloride, you're going to end up with 2 moles of chloride ions. So we need to times it by 2. This one just gives us 1, so that is the number of chloride ions as well. This one just gives us 1, so that's also the number of chloride ions. So now we've done that, we can see which one contains the most, which is B. A sample of 2.18 grams of oxygen gas has a volume of 1,870 centimetres cubed at a pressure of 101 kilopascals. What is the temperature of the gas? So we've got to start by working out the moles of oxygen. So we're going to do mass over mR. Don't forget, oxygen is diatomic, so it's going to have an MR of 32. Okay, once we've worked out the moles, we can use the ideal gas equation to work out temperature. Remember, your pressure has to be converted into pascals. And your volume has to be in metres cubed. It's come in centimetres cubed, so we need to divide it by 1,000,000. N is what we worked out in the first equation, and the gas constant's given to us in the question. That gives us an answer of 334 Kelvin, which is B. Okay, for these ones, we need to work out which of these samples of gas contains the largest number of molecules. So if we work out the number of moles, that's going to be directly proportional to the number of molecules. We would have to times by Avogadro's number to find out the number of molecules. But as it's directly proportional, just working out the moles will get us the right answer. So we're going to use this arrangement of the ideal gas equation. All of the pressures are given to us in pascals. Just watch those two, because those two will need converting into metres cubed. Decimetres cubed to metres cubed is a factor of 1,000, so you need to divide them by 1,000. So if we go through, we can work all of those out. The first one is 0.2, the second one is 0.24, 0.21, 0.16. And the question asks which is the largest, so it's going to be B. Silver oxide, Ag2O, can be reduced by passing hydrogen gas over the heated oxide. The maximum mass of silver that could be obtained from 2.32 grams of silver oxide is... Right, so we're going to start by working out the moles of silver oxide. So we're going to do mass over mR. Okay, be a little bit careful here, because the formula is Ag2O. For every 1 mole of this, you're going to end up with 2 moles of silver. So we then need to work out the mass of silver, and that's going to be the moles times the relative atomic mass. And that corresponds to answer D. The percentage of copper in a copper 2 salt can be determined by using a thiosulfate titration. And we know we're starting with this mass of the copper salt. It was dissolved in water and added to an excess of potassium iodide, liberating iodine according to the following equation. So all of our copper has reacted to form iodine. The iodine liberated required 24.5 centimetres cubed of a 0.1 solution of sodium thiosulfate, so that's this one. So we can work out the moles of sodium thiosulfate, and that's the only thing we can do to start with. Okay, so we know that 2 moles of sodium thiosulfate reacted with 1 mole of iodine, and that 1 mole of iodine was formed from 2 moles of the copper ions. So what we can say from that is that the moles of the thiosulfate are going to be equal to the moles of the copper ions. Once we've got that, we can work out the mass of the copper. Once we've got the mass of the copper, we can work out what percentage of the copper salt was actually made up of the copper. And we do that by doing the mass that we've worked out of the copper ions divided by the original mass that was weighed out, and then we're going to times it by 100. So we end up with 51.0% mass by copper by mass, which is answer B.